So students, you will allow me say the following before we begin this lesson. One, I have uploaded all the materials that you need on the website. If you go to the Blackboard, you'll be able to see what you require for this particular course, especially the course outline, because I will not go through the course outline. You are not new students. The rules are the same, but I have given a detailed course outline, and I've also shown what will be learning at which particular week of the semester. Therefore, I would actually refer you to the website for that information. I also want to say that this, as one of the students said, and as I was informed, this is a directed course. And therefore, we are going to do half the lectures. There is a way through which we can do all the lectures within that half, but I am going to give you the best that you need for this particular course. For today, this is actually the second week, and therefore I am supposed to have given you enough work until this time. If you look at the course outline, you will realize that at around the fourth week, in the fourth week, you'll be having quiz 1, and also there's an assignment attached to it. Now, for this reason, I am going to give you enough and ensure that you also have enough practice for you to be able to tackle any examinations that come by. So I'm going to share the first slide or the first lecture that I want to give you. I will try as much as possible to actually handle 2 lectures today because we have enough time. Now, this is a double lesson, and therefore there are 2 sessions. The 2 sessions means that I am going to look like, it's like I'm going to give 2 lectures. Therefore, your class attendance is going to be taken twice, and I'll be doing this at a particular break as we continue learning. When I look at the number of students that we are supposed to have, there are some students I have met before, like Nancy Ayubu. I think I have met her before in our class. I've also met, there's another student I've seen here that I've met in another class. So I'm not new to some of you, but I could be new to others. So allow me load the presentation for today, and we are going to be introducing ourselves. The first thing is to introduce ourselves to the analytical separations. So that is what I'm just about to load. So are you able to see the screen that I'm sharing now?
Yes.
Thank you very much. So this is introduction to analytical separations. I want to take you through this, and after that, we can briefly look at the solvent extraction. So why do we need the separations? We say that separations are extremely important in synthesis, in the industrial chemistry, in the biomedical sciences, and also in chemical analysis. And what happens in separations? In separations, we have isolation of the analyte from potentially interfering constituents, and these constituents could be impurities. So we need to get the analyte in its pure form, and therefore when we get an analyte in a matrix mixture of other interfering substances, we need to separate so that that target analyte or the analyte of our interest is going to be in pure form. Now, the separations can be complete or incomplete. We can say that they can be incomplete, they can be complete or partial. And if you look at what I have shown here, I have shown an example of a partial and complete separation. And I'm just trying to get a pen. So if you look at these, this is an example of a complete separation, whereby here you have so many substances, and in the complete separation here, these substances are going to be such that each of them is going to be isolated. Like in this matrix mixture of many substances, we do have the red ones. We do have, what color is this in the triangle? Is it green? Ladies in the house, what color is this? What color is this?
Green.
Green, eh?
Yeah.
And then we have yellow. So in the complete separation, you pick all the green alone, you pick all the yellow alone, and the red alone. Now in the partial separation, you are only picking that which you are interested in, and then you can leave the rest alone. Like in this particular case, we do have a separation whereby we are only interested in the red. And the moment we are able to isolate the red, then every other thing is left unseparated, because we have already achieved what we wanted to get from the separation. We move on, and we say that the main objective of an analytical separation is usually to eliminate or reduce interference so that we can achieve quantitative analytical procedure, so that quantitative analytical information can be obtained from complex mixtures of substances. Now, there are various methods that we can use for separation, and here we have categorized them into three. One, we have what we call the mechanical phase separation, then we have chromatography, and then we have what we call electrophoresis. In the mechanical phase separation, we have sub-methods, and the first one here is precipitation and filtration. You allow a substance to precipitate, and after precipitation, to solidify, you form some solid from a solution, that is, you are precipitating. And then after the precipitation, you can do some filtration. And this is best suited in those substances that differ significantly in their solubility. Then we have another one, which is distillation. And when we are doing distillation, we are taking advantage of difference in the boiling points of the substances that we want to separate. And here we can talk about volatility of the substances. Then we have extraction. Extraction here, we are going to actually be discussing solvent extraction shortly. And here we are looking at difference in the solubility of the substance in two phases. That's why we are saying two miscible solvents. So we have one phase and another phase. I'll be discussing that more when we go to solvent, but they are supposed to be immiscible solvents, between two immiscible solvents. Then we have what we call the ion exchange. This one takes advantage of difference in the interactions with some ion exchange materials. And for example, here, it is the ion exchange resin. Now, I can see students are sending names here. I want to imagine that this is a form of taking your attendance. Do not worry about this. I'll call you verbally at some point during this lecture, but I appreciate that you have already recorded it in a chat, but I will revisit this at some point in our lecture. Thank you. Now, the other method is what we call chromatography. Actually, chromatography forms basis of our course. And here we are looking at difference in the movement of a solute through a stationary phase. Chromatography is something that we started learning way back even in high school. For those of you who can remember, I think in Form 1, this one was done. And I think to some extent in your primary school, whereby we would get some flower extracts and use them to do some of the chromatographic techniques. And then the third one is electrophoresis, whereby we are talking about a difference in the migration rate of a charged species when this is placed in an electric field. So let us look at separation by precipitation. Separations by precipitation require large solubility differences between the analyte and the potential interference. And many precipitating agents have been used for quantitative inorganic separations, and we are going to be looking at a few of these. Now, separations based on the control of acidity of the matrix mixture. There are enormous differences among the solubilities of hydroxides, because when you talk about hydroxides, now this is something that governs the pH of a particular medium. So the solubilities of oxides, hydroxides, hydrous oxides, and acids of various elements, they differ a lot. So the concentration of hydrogen or hydroxide ions in a solution can be varied significantly. And this variation can be controlled by the use of buffers, so that we have those that are near neutral, those that are extremely acidic, and those that are extremely basic. We are going to mention some of them. So many separations based on pH control are in theory possible, and in practice, they can be grouped into three categories. And this comes to what I've just mentioned. So number one, those meant in relatively concentrated solutions of strong acids. So we are talking about separation in a strongly acidic media. Number two, we may have those that are made in buffered solutions, so that we can have intermediate pH values. You are maintaining it in a particular pH range. And we also have those that are made in concentrated solutions of either sodium hydroxide or potassium hydroxide. And these are the ones that we say are in strong basic medium. And if we were to give examples, of some of the separations that can be achieved by the control of acidity. For example, if you look at, let me pick my pen again. If you look at what we have here, this is hot concentrated nitric acid. Now, this means that we are doing separation in a strongly acidic media. And for example, you have tungsten 6 can be precipitated. Those are the oxides of tungsten 6, tantalum 5, niobium 5, silicon, tin, and antimony. All these ones the oxides of these species can form precipitates. While those of the metals that we have not mentioned here may not actually form precipitates in such an acidic medium. Now here we have an ammonium chloride buffer, and then you can see iron 3, chromium 3, and aluminium 3 can effectively precipitate, while those alkali and alkaline earth metals of manganese, copper 2, zinc, nickel, and cobalt will not precipitate. Then we do have here what we call acetic acid and ammonium acetate buffer. This is acetic acid, it's a short form, and this is ammonium acetate buffer. Then when you have that kind of a buffer, then you expect to separate like iron 3, chromium 3, and aluminium 3, while those oxides that are on this side will not be precipitated. And the same thing applies to here, where we have a strongly basic media. Then we are able to precipitate the iron 2 and most +2 ions of the rare earth metals can be precipitated. Now we go on. When we come to proteins, we can effectively precipitate proteins by using some salts. So a common way to separate proteins is by adding a high concentration of a salt. And this procedure is called salting out the protein. And why do we do this? The solubility of protein molecules will show a complex dependence on the pH, temperature, ionic strength, the nature of the protein, and the concentration of the salt used. And at low salt concentrations, the solubility is usually increased with increasing salt concentration. And we want to illustrate that by using this protein here. Now, when you have a protein, we want to illustrate how it can be precipitated by the use of ammonium sulfate. So you have a protein here, you have a protein here, and now this protein has got very suitable functional groups. And for example, here, we are showing how that protein is interacting with water molecules. And in the interaction with water molecules, remember water is an aqueous, is an hydrophilic molecule. And therefore, if you look at, for example, this group here is favorably going to interact with a water molecule. In other words, the amine groups and the carboxylic groups of the molecule of the protein are going to favorably interact with the water molecules. And you can see the interaction here is leading to the formation of what we call a hydration layer. Now, this hydration layer leads to the protein being soluble. So if you introduce any compound here or any chemical here, which interferes with this hydration property of water, then it means that the solubility of this protein is going to be negatively interfered with, in the sense that this hydration layer is not going to be formed. And in our case, we are using ammonium sulfate to interfere with the formation of the hydration layer. And this is illustrated in this slide here. So you can see what is happening here is this ammonium sulfate here has come in to actually break down or disrupt the formation of the hydration layer. And once that is formed, then this protein is going to be precipitated. It is going to lose the solubility property, and therefore in the process it is going to precipitate. So this is actually what we are calling sorting out, and we are illustrating it using the ammonium sulfate. So once that happens, we can now separate either using the precipitates now can be dissolved in buffer. And once they are dissolved in buffer, then we can use various methods of separation, like the column chromatography, ion exchange chromatography, affinity chromatography, gel permeation chromatography. We'll be looking at these various types of chromatography as we go on in this course. Now, why do we use ammonium sulfate, for example, in salting out? Why do we use it to induce the precipitation of proteins? One, it is a cheap salt, readily available, and its large solubility in water. And then it has relative freedom from temperature effects, and it has no harmful effects on most proteins, in the sense that it will not cause either denaturation of proteins or making them lose any of their desired properties. The salt concentration at which a protein precipitates differs from one protein to another. And therefore, the sorting out can be used to fractionate proteins. And a good example is when we say that 0.8 molar of ammonium sulfate is able to precipitate fibrinogen, which is a blood clotting protein. But a concentration of 2.4 molar of the same ammonium sulfate will be required to precipitate serum albumin. So these are two different proteins, but they require different concentrations of that particular compound, different concentrations of ammonium sulfate to be able to precipitate. Now, proteins are commonly least soluble in their isoelectric points. And what are these? What is an isoelectric point? This is the point at which the net charge of that protein is 0. We say that the isoelectric point is the pH of a solution at which the net charge of that protein is 0. And therefore, a combination of high salt concentration and pH control is desired to achieve adequate salting out. However, care must be taken with some proteins because this ammonium sulfate can denature the protein, and therefore alcoholic solvents are sometimes used in place of salts. The other one is what we call filtration. This is now filtration I'm talking about. Separation of solids from liquids. And filtration is something that has been done even from low levels of education. And there are two types of filtration. One is gravity and the other one is vacuum. You know, gravity is just when you take a filter paper and you put it into some separating funnel, and then you pour the material, and the material, the solid is going to be stuck on the filtration, on the filter paper, while the liquid goes down into the collecting jar. But when you talk about vacuum, you can see here, this is connected to some suction force, which is going to force the liquid come down and leave the solid material on the platform above. Now, then we have separation of species by distillation. And we said that distillation is when they used to separate volatile analytes from non-volatile analytes. Those whose boiling points are very low will actually evaporate and leave those whose boiling points are high. So this distillation is based on the difference in the boiling points of the materials in the mixture. If you have methylated spirit, and then you have maybe mixed it with the water, and you just want to remain with the water, you can leave it in the open at room temperature. The spirit is going to evaporate, and you are going to be left with your water. In the event that you are also interested in collecting the methylated spirit, then you need to come up with a way of tapping the vapors and allowing them to condense in some chambers, whereby it's going to collect as a liquid. Distillation is widely used in organic chemistry to separate components in mixtures for purification purposes. And there are various types of distillation. One is what we call the vacuum distillation, which is used for compounds that have very high boiling points. Lowering the pressure to the vapor pressure of the compound of interest will cause the boiling point, will cause boiling, and it is often more effective for high boilers than raising the temperature. The other type is what we call the molecular distillation, which occurs at very low pressure, like 0.01 torr, so that the lowest possible temperature is used with the least damage to the distillate. Then we have this one, which we are calling pervaporation. This is a method of separating mixtures by virtual volatilization through a non-porous or porous membrane. Then there is the flash evaporation, which is a process in which a liquid is heated and then sent through a reduced pressure chamber. The reduction in pressure causes partial vaporization of the liquid. And then in this particular introduction, we can look at what we call fractional distillation. I think fractional distillation is something maybe you have done in your high school or lower levels. And I gave an example of whereby maybe you want to separate maybe ethanol and the water. Because of the difference in the boiling point, you can easily collect your ethanol at around 78 degrees Celsius. But water is only going to be boiling at 100, so it's going to be left in the flask. You can see here, this is where the distillate is being collected. This is where the distillate is being collected. The residue is going to be here, where this is where we are going to have the material whose boiling point is high. This is where we are going to collect the material whose boiling point is low. So for purposes of introduction, I would say that that is what we have. Any questions so far, students? Are you there, students? I need to hear you. Are you following?
Yes, we are.
Very good. So allow me take the record of attendance. This one I'm going to do online. Just a moment, so that now I can move to the second lecture. We have adequate time and I can see we'll be able to cover the content that was intended for last week and this week. So allow me to take the attendance now. Precious Amai, are you in? Precious Amai? Is Precious in? Okay. Nancy Kageni.
I'm present, sir.
Okay. Kelvin Kigo. Kelvin?
Present. Yes, sir.
Yeah, I saw you join, so I'm surprised why you're not responding.
No, I'm here.
Evelyn Kyoko.
Present.
Okay. Esther spoke to me. I think I understand. Then we have Brenda Koech. Is Brenda in? Okay, I have marked her absent. Brenda Mutwiri. Brenda Mutwiri, absent also. Mercy Nyamwea.
Present.
Great. Whitney Nyasagare.
Present.
Is there a student whose name I have not called?
Yeah,
Mine.
Who is? Yeah. This is when
Mine. Ivy.
Ivy.
Kerubo. Yeah.
Are you registered?
I'm not yet registered, but there's a problem with my CX, but I'm supposed to register either today or tomorrow.
Okay, just a moment, then I take your details. You are Ivy who?
Kerubo Ugoti.
What is your registration number?
664
664
105
105.
105.
Okay. And any other student?
Yeah,
Ye-
me.
Your name?
Brian. Sorry.
Brian.
Brian Dirango
Brian
Dirango Moshero.
Dirango. Mushero.
Yeah.
What is your number, Brian?
663
63
973
9
73.
73. Any other? Okay, I will keep your details. Then I will regularize your attendance once you also regularize your registration. Is that okay?
Yeah, that's fine.
And please inform your students that any session you miss actually counts for 2 sessions that somebody is absent. Because remember, these are double sessions. Okay. Thank you. Now I want to go to something different. So I will put down this and upload another lecture. Ayubu, did I call your name? Nancy Ayubu.
Yes, sir.
Did I call your name?
Yes, it's Nancy Kageni.
And there's Nancy Muroki.
Yeah, it's me, Nancy Kageni Muroki.
Oh, you are Nancy Kageni Muroki.
Yes.
Okay.
Yeah.
So that is the second one. I hope you can see. I want to introduce you to solvent extraction. You can see the new slide that I have introduced.
Yes.
Very good. Now, this is actually what I intended to teach this week. And what I have just finished is what I would have taught last week. So you can see it's like we have compensated, haven't we? So when we talk about solvent extraction here, we talk about the transfer of a solute from one phase to another. When we talk about from one phase to another, for example, we can give an aqueous phase. An aqueous phase, we can call it phase 1, which, for example, we can give as water, and an organic phase. We can give an organic phase, for example, toluene or ether or such kind of organic solvents. Now, at this point, we have talked about a solvent and a solute. Now, what is the difference between a solvent and a solute? Yes. Any student to give us the difference between a solvent and a solute? Students, let's talk together.
A solvent is a substance in which a solid is dissolved.
Mm-hmm.
Well, a solid is like the solid now which is being dissolved in a solvent.
Okay. Okay, that's a good try. Any other definition? Any other distinction between a solvent and a solute?
Can we say that the solvent is the major component, whereas the solute is usually the minor component?
Actually, that is the correct definition. When we talk about a solute and a solvent, in most cases, we tend to think about the solute being the solid and the solvent being the liquid. But if we want to understand, you can talk about the one that forms the smaller percentage as the solute, and the one forms a larger proportion as the solvent. Now, if we stick to a solute as being a solid and solvent as being the liquid, somebody would ask, supposing that we have something like HCl, and then we have water. You know, both of these are liquids, isn't it? So when we are making a solution of HCl, normally we realize that this one will carry the larger proportion while this one will carry the smaller proportion. Therefore, this one becomes the solute, this one becomes the solvent. Now, this is for purposes of just defining what a solvent is and what a solute is. Now, in this particular case, we are talking about the solute, which is actually distributing itself into two different phases. For example, you may have a salt or a solute, we call it S. Where is this writing going to? Okay, let me pick something that I'm sure it's not. So we have a solute. Where are my writings going to? A vanishing pen, spotlight, no. Let me pick again a pen which doesn't go. Why is this pen of mine vanishing? There's something I don't understand. Because I want to write something that I can refer to. Okay, nevertheless, I will explain. I think I have picked a better pen now, just a moment. Good. So you have a solid here, which we can call it a solute. And now this solid of ours, we have a jar here, and this jar has two different faces. One, we have a face there, and we have another phase up here. Now, once we put our solute inside here, some of it is going to be here and some of it is going to be here. So we say that this particular solid is going to distribute itself between the two immiscible liquids. Now, this is phase 1. This is phase 1. This is phase 2. So if we know the amount of a solid that we have here, which we have already put here, then we know for sure some of this solid is going to be in phase 1, the rest is going to be in phase 2. So we can actually express this as fractions. Some fraction 1 is going to be in phase 1, and the fraction 2 is going to be in phase 2. Now, once we know that, then we can ask ourselves, what is the sum of fraction 1 and fraction 2? What do we get when we have fraction 1 and fraction 2? We know that fraction 1 plus fraction 2 is supposed to give us what? 1. Do you agree with us? Because we have taken the total sum of the fractions of the solids that have distributed themselves in the phases that we have. So when we take the total sum of the fractions, we are supposed to get 1. Number 2, if we know the concentration in terms of molarity, or the number of moles here, if we know the number of moles, then we can say some moles are going to be in phase 1 and some moles are going to be in phase 2. And therefore, for us to get the concentration, we know that concentration is moles per unit volume. But now some moles are going to be in phase 1, while some moles are going to be in phase 2. I don't know whether students, you've come across what we call mole fraction. Have you ever come across mole fraction? Students, am I talking a lot? Hello, are you there?
Yes, you're here.
Have you ever come across something we call mole fraction?
Not really.
Okay, so look, I have said that if the amount here, we are looking at it in terms of moles of a substance. So some moles will actually be in here, some moles will be here, and some moles will be here. So for us to get these moles very well, we can talk about the fraction, the mole fraction in phase 1, multiplied by the total number of moles, and the mole fraction in phase 2 multiplied by the total number of moles. So that is going to give us the total number of moles that we have. If, for example, we have 5 moles, the total is 5 moles, then only 2 moles are going to go here, and the 2 moles are going to go down, and the 3 moles are going to go down here. Then in terms of mole fraction, we can say that 2 all over 5 is in phase 1, and 3 all over 5 is in phase 2. And you can see these fractions are actually going to give us, if you add the 2, then you're going to get a total of 1, which is represented by the total of the 5 moles. I'm explaining because we need it to understand something here. So look, the principle of solvent extraction, we say that the partition of a solid between 2 immiscible phases is an equilibrium process, which is governed by the distribution law, and we have explained what happens. You put a solute somewhere, and then this solute is actually going to distribute itself by fractions into two or into the various phases that we have. Here I am using two phases. The phases may be more than two. But for purposes of this explanation, I'm only going to confine myself to two phases. So if the solute species is allowed to distribute itself between water and an organic phase, water is an aqueous phase, organic phase is an organic phase, then the resulting distribution may be written as there's going to be an equilibrium of these two. So we have S1 and S2. An equilibrium is going to be established where the subscripts 1 and 2 refer to the aqueous and the organic phases respectively. Now, the ratio of activities for the solute in the two phases will be constant and is dependent on the total quantity of the solute, so that at any given temperature, the K is going to be equal to AS2 over AS1. When we talk about AS2, we are talking about the activity of the solute in phase 2 divided by the activity of the solute in phase 1, which is also equal to the concentration of the solute in phase 2 over the concentration of the solute in phase 1. In chemistry, when we are using the square brackets, we actually mean a concentration. Note, under many conditions, the molar concentrations can be substituted for activities without any serious errors. And that is why we are saying that we can actually use the concentrations instead of activities. And in the discussions that are going to follow, we will actually not be using the activities, but we'll be using the concentrations of the solutes in the different phases. And the equilibrium constant is actually what we call the partition coefficient. Now, the importance of this distribution law is that it provides a guidance on most efficient way to carry out an extraction. And it also allows us to calculate the concentration of an analyte remaining in a solution after a certain number of extractions. And when we follow this, we'll be able to tell if you want to extract a lot of a material, do you need to use smaller quantities many times, or you just need to use large quantities once? We are going to demonstrate that as we continue. So you can see this is equation 2 because it is similar to the equation that we have here. Now we continue. For a simple system described above, the concentration of S remaining in phase 1 after n extractions with a second solvent is given by this equation here. And the fraction remaining in phase 1 after n extractions is given by this. We are talking about this equation actually, where Qn is equal to all this. I'll be able to explain what this is. Now, this Q here is a fraction. V here is volume 1, the volume in phase 1. K is the partition coefficient, and V2 is the volume in phase 2. N here stands for the number of extractions that you have done. And we are going to see how we are going to be arriving at this equation in the next few slides. So I'm going to be explaining slowly. So we are going to look at equations, especially the relationship here, and let's see how we will eventually arrive at this. So deriving this equation, and then we are starting with a particular assumption here. Supposing that you have a solute in volume 1, V1 meaning that This is phase 1 or solvent 1, which in our case is the aqueous phase, and we are giving the aqueous phase as water, which is extracted with another solvent, solvent 2, and in this particular case, solvent 2 is toluene. Toluene is a good example of an organic phase. Now, let M be the number of moles of S in the system. Now, when we say number of moles of S in the system, here we are talking about, let me pick my pen, just a moment, I pick my pen. Now, this pen is going to disappear. I want to pick my pen. Now, when we talk about M being the moles of S in the system, we are saying that the S or moles, let me write. Here we are talking about moles of S in water plus moles of S in toluene. That's what we mean when we say that M be the number of moles in the system. Now, when we talk about let Q be the fraction of S remaining in phase 1, you know, phase 1 is where we have water, and phase 2 is where we have toluene. Now, what we need to understand here is this. When we say Q is equal to moles, fraction in water. That is the fraction in water. How many fractions do we have? We have 2 fractions. There's a fraction in water and there's another fraction in toluene. So if Q is the fraction in water, then the total sum of the fractions must be 1. Therefore, we must ask ourselves, what is the fraction in toluene? The fraction in toluene must be 1 minus Q is equal to fraction in toluene. Any question? Is it understood? Hello?
Yes, it's understood.
Good. So from this, then we can ask ourselves, what are the concentrations of each of these? The concentrations are going to be, if we take the fraction in water multiplied by the total number of moles, then we are going to get the concentration in water. All right? So if you take Q, which is the fraction in water, and we multiply by M, this is going to be the concentration of S in water. And this is actually what we are saying, you know, because water is phase 1. Water is phase 1. That's why we are talking about like this. That's why we are talking about this one. This actually is not, it is moles, not concentration, moles. It is going to give you the moles of S in water. And for us to get concentration, is equal to moles divided by volume. And that is where now equation 1 comes. That's why equation 1 comes. You can see the concentration of S. When I talk about this, let me just go back here. When I talk about this concentration here is supposed to be the concentration of S1. Therefore, we are saying that when we talk about the concentration of S1, this is equal to In fact, I can do it like this. Are you able to see the new window that I've opened?
Yes.
Can you see a new window? Can you see something I've highlighted in black?
No.
Okay, I understand why you can't see it. Then let me explain the equation. Now we are talking about equation 4. This Q that you can see here is the fraction of S in water, the way we have explained it here. And this M is the total number of moles. So when we get this, we actually get the mole fraction of S in water. Then when we divide by the volume, V1, then we get the concentration of the solute in phase 1. And it is giving us that. If there's a need for me to explain anything more, please you let me know. We have time. Then I move on. The fraction of the total solute transfer to phase 2 is 1 minus Q. This one I explained because the total fractions must be equal to 1. And if Q is the fraction in water, then 1 minus Q should be the fraction in the other phase, which is toluene. And therefore, we can look at the molarity in phase 2 is equal to 1 minus Q, which is the fraction, multiplied by the number of moles so that you can get the mole fraction. And then you divide by the volume in phase 2. I'm talking about equation 5. So that is going to give us S2. Now, if we have the expressions of S1 and S2, then we go back to equation 2. We go back to equation 2, whereby we are saying K is equal to S2 over S1, which is what we are doing here in equation 6. Is there a question? Are we okay? Okay, good. Silence means we are doing well. So then when we have S2 over S1, then we simply take what we have obtained in equation 4 and in equation 5. If I am to just pull equation 4 here, you can see equation 4 is here. You can see equation 4 here is here. So you have S2, which is described by equation 5, which is 1 minus Q into M over V2 divided by S1. S1 is what we got in equation 4, which is Q over M. And what you get, actually, what you get is equation 7, and you'll realize that M and M will cancel out, and the equation is going to look like as shown in equation 8, whereby we have V2Q in the denominator, then you have 1 minus Q into V1 in the numerator is equal to K. So we can multiply both sides by V2Q, which is being shown here. Multiply both sides by V2Q will give you the equation as shown in equation 9. And once you do that, then you can remove the brackets, because you can see on the right hand side we have brackets, and this is what you're going to get. And then you collect the like terms together. These Q's are collected together, you get equation 11, and then you can factor out Q. When you factor out Q, you get equation 12. And when you make Q the subject of the formula, this is what you get, equation 13. Now, if you look at equation 13 and this equation here, can you see some resemblance? Equation 13, let me pull this one to where we have equation 13. Compare these two equations. Can you see some resemblance?
Yes.
Yes.
Yeah, it means that when you raise Q to any power, you also raise the other side to any power. And that is going to be like that. So what happens after this? If the faces are separated and a fresh toluene is added, you know, here you have done the first separation, which is actually given by this equation. Then you do another separation, which is going to be given by the same equation. So it's like you have the same equation multiplied twice. This is the second separation. So if the faces are separated and fresh toluene is added, the fraction of solute remaining in the water at this second equilibrium will be just squaring the equation 13. And if you do a third one, then you are going to have power 3. If you do a fourth one, you're going to have a power 4. So that after n extractions, each with volume 2, the fraction remaining in the water will be Q to power n, and the right hand side will also be raised to power n. Again, this is the same equation 3 that we saw. Then you are raising to the respective powers. And I want to illustrate this one with an example here. And the example is solute A has a partition coefficient of 3. So K is 3 between toluene and the water, with 3 times as much in the toluene phase. You know, when you say 3 times as much, now you can get the fractions, if you so wish. Now, supposing that 100 mils of a 0.10 aqueous solution of A are extracted with toluene. What fraction of A remains in the aqueous phase, A, if one extraction is done with 500 mils, and B, if 5 extractions are done with 100 mils? So here you just isolate what you need. I have actually done this, and you can see for part A, you substitute, you simply substitute. And you see in one, what do you call it? One separation for part A, one extraction with 500 mils is performed. So you substitute. V1 is 100 because it is here. V1 is 100 and the V2 is 500 in part A. In part B, V1 is 100, V2 is also 100. So you can see if you do one extraction, okay, somebody is in the waiting room. If you do one extraction, then this is what you're going to get. But if you do 5 extractions, now with a smaller volume, I want you to see what is happening. I want you to see what is happening in part A and B. If one extraction is done with 500 mils, and if 5 extractions are done with 100 mils. So in part A, you are doing one extraction with a large volume. In part B, you are doing 5 extractions with small volumes. So let us see the fractions that are remaining. When you do one extraction with a large volume, the fraction remaining is 0.0625. If you do 5 extractions with small volumes, then the fraction remaining is 0.0098. So this is what is remaining. It means that if you want to get what you have already extracted, you subtract 1. You subtract these values from 1. For example, if we want to get how much we have extracted here, we need to get 1 minus 0.0625. And what do we get? Let me just get my calculator and tell you how much we'll have extracted. So this is a, just a moment, I pull my calculator. Oh, sorry. You get 1 minus 0.0625, and you'll have extracted so what you are getting here is equal to 0.9375. 0.9375. Now, this other one, you are taking 1 minus 0.00098 to get what you have extracted. So when it comes to this, you get 1 minus 0.00098. And what you are getting will be 0.99902. So in both cases, you can see what you have extracted. When you are using a large volume and doing it once, this is how much you are getting. When you are using a small volume and you are doing it many times, this is what you are getting. You know, the idea is to extract as much as possible. And you can see here, you are almost close to extracting 1. You are almost extracting 1. While here, it is not close to 1. So you can see that it is more efficient to do many small extractions. That's what I wanted to illustrate. Okay. Another example is here. The distribution constant for iodine between organic solvent and water is 85. The distribution constant is what we are calling the partition coefficient, the K. Find the concentration of iodine remaining in the aqueous layer after extraction of 50 mL of this concentration with the following quantities of organic solvent. So this is V1 for part A, this is V2. For part B, this is it. So what we need to look at, in part A, you have 1 extraction, but you are using 50 mL. In B, you have 2 extractions, but you are using 25 mL. In part C, you have 5 extractions and you are using 10 mL. I have done for, I think, part 1 only, and you can see the amount remaining is this. You just substitute. For example, here we have V1 is 50, V2 is 50. Of course, the K is 85, it is given. And this is the concentration given actually here. This concentration is given here. This concentration is given here. That's why we are multiplying by 10 to the power minus 3. So you can see this is the concentration remaining. Now, if you look at the second one, where now you are doing 2 extractions with 25 cubic centimeters. So you will actually have a reduced volume, and with a reduced volume, actually it's going to be Q2 is equal to all these squared, but then this is going to be, V2 is going to be 25. You are going to get something. And then in part C, you do 5 different extractions, but with smaller volumes. So you can see moving from A to C, you'll actually be getting different fractions remaining, or different concentrations remaining, or different quantities remaining. And now if you get different quantities remaining, then you can ask yourself, how much have I extracted? How much have I extracted? Okay. So you'll be able to, you can do the rest. So what follows are exercises that you students can actually try. Like if the partition coefficient is 10, what fraction remains in 100 ml of water after 1 and 5 extractions with 20 mils of toluene? Another exercise here is that the distribution coefficient of Z between n-hexane and water is 5.85. Calculate the percentage of Z remaining in 25 ml of water that was originally 0.0550 molar in Z after extraction with 125 cubic portion of n-hexane. Again, you substitute. This is one extraction. These are very good exercises that you can try. Now, if you wish to extract aqueous benzoic acid into hexane, is it more effective to adjust the aqueous phase to a pH of 3 or a pH of 8? Explain. And then the other thing is the pH effects. Actually, it is related to this exercise here, the pH effect. And we can say that the charge on a basic acid or solute changes as the pH of the solution changes. A neutral solute is more soluble in organic solvents, while a charged solute is more soluble in aqueous layer. And consider a basic amine B. Its partition coefficient between aqueous phase and organic phase is given by this. This is similar to some equations that you have seen before. And the conjugate base of the conjugate acid of B dissociates according to the equation. Then you have an acid here, which is dissociating to give you a conjugate base and releasing some hydrogen ions. And then when you write the dissociation constant actually is a division. You actually get the product of the concentration of the products divided there by the product of the concentration of the reactants. And you can see here, the products are a B1 and the H plus, and that's why we are taking their concentrations here being the numerator. The product of the concentrations of the products divided by the product of the concentration of the reactants, which is giving us equation 17. Now, when we assume that the conjugate acid is only soluble in aqueous phase 1, the distribution coefficient will be defined as the total concentration in phase 2 divided by the total concentration in phase 1, which is actually giving us equation 18. And if we do some substitutions of equation 16 and 17 into equation 18, then you get an equation 19. It can be derived the way we derived the other equation, only that I didn't want to bother you with so much of the deriving. Now, this AB is the fraction of weak base in the neutral form, and B is in the aqueous phase. And we need to note, when dealing with a solute that has more than one chemical form, such as B and the BH, the distribution coefficient D is used. And there's an example here. This example is done. We have done this example. You can look at it. Example, you can just, it is done. But I have only done first part. I have not done the second part. So you follow it and see whether you can do the second part. So I can say that that is also end of this lecture. It's the end of this lecture. Any questions? There's a student that has just
Yes,
joined.
I have a question.
Yes.
I have a question.
Yes,
On the first section that we did,
the first
you
section,
said-
yes.
not the first section, the first question on this lecture that you did.
Or the
for
first
one
question that I did.
Yeah.
Okay,
The second part.
let me go there. Let me go there. I want to go to, this is it. Is it this one?
Yeah.
Mhm.
Yes. On the second part of the question, you said that the moles extracted, right, was 1 minus 0.0625.
Yes.
I didn't get that part because from before you said that Q is the fraction of moles in phase 1,
Yes.
and 1Q is the fraction of moles in phase 2.
Yes.
So how are the extracted moles related to the phase moles?
Now
Fractional
look,
moles?
look at the question. A solute A has a partition coefficient of 3 between toluene and the water, with 3 times as much in the toluene phase. Now, supposing that 100 ml, this is V1, okay, of a 0.01 molar of aqueous solution of A are extracted with toluene. What fraction of A will remain in the aqueous phase? Now, if it remains in the aqueous phase, it means that what is not remaining is what has been extracted. Okay?
Yeah.
So that's why the difference here is the one in toluene, because we are transferring it there. Do you understand?
Yeah, I've gotten it. Thank you.
Okay. Another question? There's a student who I saw joined after I took the attendance. I can't remember who the student was. Precious Amwani, did you join? Are you here now?
Yes, I'm here, sir.
Yes, because we had marked you absent. Huh?
Sorry, I was a bit late.
Okay, now let me mark you present. Okay. I've just marked you present. Okay.
Thank you.
Let me update it. Any other student who has just joined, so that we can pick the total attendance. This one counts twice, because of the 2 sessions that we've had. Any other questions, students? Well, then, having no other questions, I can say that we have really finished very early.
Sir,
Yes, yes.
will you be able to upload the video of this class on Blackboard?
I will do that. In fact, after this, I'm also going to make the notes available to you, because they are already on the Blackboard. Then I'm also going to avail the recording. Is that okay?
Okay, thank you.
Okay, so we can say bye, but we need to agree on this. I was actually told that this class was supposed to be face-to-face, and you are telling me that it is supposed to be online. Can we see clarification in the course of next week, and then we advise each other accordingly? Students?
Yes, we can do that.
Yeah, let us give each other next week to seek further advice. But I have no problem with the online, and I have no problem with the face-to-face. Okay. The other thing you need to note is that this is supposed to be partial, isn't it? And that means that if we meet this week, we may not have to meet next week. We may have to meet that other week. but I'll advise you. Is that okay? Hello?
Yes,
Okay.
Yes.
Okay, thank you. So having said that, and seemingly having no other questions, we can end the class at this point. So have a very good weekend. Bye-bye.
Bye.
Bye.